Okay, so now we're looking at the Incredibles one. So this one has a lot of steps to it, but hopefully it's not too bad. I think each individual step, if you kind of try to tackle this at one time, it would be a lot. But if you break it down, hopefully it's not the worst thing in the world. So we're going to break it down section by section. And part one is the initial fall. So this man falls a height of 94.48 meters until he's caught. How much time does it take for him to fall this time? So we're going to assume that he starts from rest and that he's in free fall, which means the only force acting on him is gravity, which means the acceleration is 9.8 meters per second squared. So if we're looking at this one, we can kind of call this a y of 0, and we can say his initial height is 94.48 meters. So if we're going to do, so then we can use our y equals y naught plus v naught yt plus 1/2 at squared equation. We said, okay, well, his final height is going to be 0. So we're saying 0 is kind of the lowest that he goes. Y naught is 94.48 meters above 0. And we said that we're going to assume that he is falling and that he just kind of drops. So we're saying that the initial velocity is 0. So that whole term is just 0. And then plus 1/2. In this case, he's accelerating downwards towards 0. So we can say negative 9.8 times t squared. So then if we want to do a little bit of math with this, we get 94.48 equals 4.9 t squared. I just kind of added this term to both sides. So we have 94.48 divided by 4.9 gives us 19.28 is equal to t squared. So that means that the amount of time it takes for him to fall is 4.39 seconds. All right, so the time that Mr. Incredible has to save him is 4.39 seconds or less. All right, so that's kind of our target time. Now we're looking at Mr. Incredible's jump. So what we're saying is assume Mr. Incredible jumps at a 30-degree angle with an unknown initial velocity. Assume he catches the man at the highest point of his jump. The highest point of the jump is a horizontal distance of 15.24 meters from the building Mr. Incredible jumps from. So what we're going to need to do is set up a system of equations. We want to know his initial velocity, and we want to know the time that he's in the air for. So let's kind of go to our situation. We'll analyze it. So we want, it looks like we need v naught and we need times. These are the two things that we need. So we need to set up equations where we'll be able to do that. So if I'm kind of coming in here and saying, okay, what do I know? I know that the x distance that he travels is 15.24, so I can list that out. So I can say x equals 15.24 meters. And we can say x naught is equal to 0. We know that he has some initial velocity in the x direction of v naught cosine of 30. Right, so if we're saying, hey, the angle is 30 degrees, we can split this up into what's happening in the x direction and what's happening in the y direction. We can say this is v naught x. I'm going to get a smaller. And say this is v naught x. That's v naught y. And we can split v naught into those two components. V naught x is the component that is adjacent to my 30-degree angle. V naught y is opposite. So if I want to figure out v naught in terms of v naught x, I can say, cosine of 30 using my trig is equal to the adjacent over my hypotenuse. So v naught x is equal to v naught cosine of 30. We do the same thing in the y direction. Say sine of 30 is equal to the opposite over the hypotenuse. So v naught y divided by my hypotenuse. So v naught sine of 30 is equal to v naught y. So that's helpful because then we have, instead of having v naught x, v naught y, and t as unknowns, we just have v naught and t as unknowns. So we're writing it in terms of what we know. Yeah. All right. And then we can say that a acceleration in the x direction is just going to be 0 because we know that we don't accelerate in the x direction. There's nothing forcing it in the air. and time is equal to something we don't know. Then if we're looking in the y direction, so in our y direction, we know that he jumps up some height, y, but we don't know what height that is. We know that y0 is something. We're going to call it 0 meters. We're going to say he goes up from 0. We said that v0 y is equal to v0 sine of 30. We know that the acceleration in the y direction is going to be negative g, or negative 9.8. And we know that the time is something. And what we also know is we're looking at a very specific point. We're looking at the highest point of the jump. So we can say that the final velocity at the, maybe I'll call it vt for v top, in the y direction is equal to 0 meters per second. So that's a big idea. All right, so then let's start kind of setting up equations and seeing what we can do. So let's look in our y direction because it seems like we have a little bit more there. We don't know anything about this final position, so this y equals y0 plus v0 yt plus 1/2 at squared, that's not really going to help us right now because we don't know this, and we don't know this, and we don't know that. So that's not a helpful equation right now. So let's look at the other equation, this vy equals v0 y plus at, this velocity equation. So we know that we have a vy at the top of just 0, this velocity at our final height is equal to 0. Our v0 is v0 sine of 30 minus 9.8 times t. Say 9.8 t is equal to v0 sine of 30. All right, so now I have one equation with two unknowns. In this case, I don't know t, and I don't know v0. So those are two unknowns, so it looks like I need another equation to do that. Thankfully, I have my equation in my x direction, and with this I know a little bit more about the position, so I can try writing my x equals x0 plus v0 xt plus 1/2 ax t squared equation. I know this is 0. So I know in this case I have x equals v0 x times t. So my x, I actually know. I know that this is 15.24 meters. I know that v0 is v0 cosine of 30 times t. So what I have is I have two equations with two unknowns. So I actually have enough now to solve. Two equations with v0 and t as the unknowns. So really I can go about this however I want. I need both v0 and t, so really it doesn't matter what order I go in. I think what I'm going to do is I'll solve for v0 first, just because I think that's the order. Yeah, initial velocities first. So I'll set this up and I'll manipulate this equation first. If you want to go 2 times speed through this part, go for it. It's not super enriching. All right, so now I have an equation for v0 and plug that in. 15.24 is equal to 9.8 t I believe I've done something wrong. I'm just going to try it again. I don't know what I did wrong. But so v naught sine 30 equals 9.8 t. So sine 30 is just 1/2. So we can say v naught equals 19.6 times t. So that's a little bit more manageable to plug in. And we have this 15.24 equals 19.6 times t times cosine of 30 times t. So we'll say 19.6 times cosine of 30 is equal, yeah, I think I multiplied them last time. Okay, that'll do it. So t squared times 16.97 is equal to 15.24. Then I can divide both sides by 16.97. So t squared .8, yeah, there we go. So then t is just the square root of that. So t is equal to 0.9485 seconds. So 0.9485 seconds. And then if we want v naught, we can just plug into this. So we can say v naught is equal to 19.6 times 0.9485. So v naught equals 19.6 times 0.9485. So v naught is equal to 18.59 meters per second. Okay, so we have both t. So v naught equals 18.59 meters per second. And then the time in the air is equal to 0.9485 seconds. All right, now we want to look to see, so the full time comes from him building up the speed and the jump. So we want to see how much time it takes for him to reach the speed of 18.59 meters per second. So we're going to say, use your initial velocity that you found from part 2 as your final velocity in this section. Let's pretend that during this section his velocity is all in the horizontal direction, and then him kicking off the building at the end is just redirecting his velocity, but doesn't actually change the amount of his velocity. So during this section he runs 4.145 meters and starts from rest. He has a mass of 158 kilograms. So what we're just saying is, like, by the end of it, let's just pretend that his final velocity is 18.59 meters per second, and that him doing that part where he jumps up is just kind of changing the direction that his velocity points and not actually changing the amount. So we're saying he's going to keep that, and he's really just kind of being redirected. Okay, so what's his acceleration? So I'm going to just list out what I know. I know that he travels a distance of 4.145 meters. I can say that his initial position is just going to be 0 meters. His initial velocity is equal to 0 meters per second. His final velocity is 18.59 meters per second. And I want to know his acceleration. So if I'm looking at this x equals x naught plus v naught t. Actually, is this equation fine? Can I use that equation? No, because I don't know time. So really with this case, my problem is I don't know what the time is. I don't know how long that takes. But we do have that one equation that doesn't have time in it. So it's kind of our least used equation, but we have that v squared equals v naught squared plus 2a change in position equation. So we can say, we can use this equation, say our final velocity is 18.59. So we can use that equation. So this is 345.5881 when you square it equals 2 times a times 4.145. 345.5881 divided by 2 times 4.145. So we get an acceleration of 41.68 meters per second squared, which seems like a good superhuman, super strength acceleration. Seems like a lot for us, but if you're superhuman, you have super strength. Seems like a good number. And then we're just going to assume that he has a constant acceleration from rest. So what's the net force? we know that net force equals mass times acceleration. So at net is equal to, we set up earlier as mass is 158 kilograms. 158 times 41.68. So he's expanding a net force. If we're assuming it's constant, we know that it probably isn't. He's not always in contact with the ground, but that's okay, it's an assumption. So 6585.44 newtons. And then how much time does it take him to run that? So that's going to be important. So the time, now we can use any one of our time equations, or equations with time in it. I'm going to use this one because it's less math, there's no time squared. So we can say the final velocity was 18.59 meters per second. Initial velocity was 0. The acceleration was 41.68. Time is what we want to solve for. So we really just have 18.59 divided by 41.68. So we'd say the time here is 0.446 seconds. Okay, and now we can put it all together. So at what time after the man starts falling does he need to start running so you can catch it? So this is kind of, I think I just wrote this badly. So what we're saying is it takes the man who's falling, it takes him 4.39 seconds to fall. So he starts up here at 0 seconds, and then Mr. Incredible catches him at 4.39 seconds. So then we need to think about what time does Mr. Incredible have to start this whole entire motion so that he can catch the man. So it takes the first part. Let's see. So the first bit of time, so for him to reach the edge of the building, is going to be 0.446 seconds. So it takes him 4.66 seconds to reach the edge of this building. So it takes, he goes from 0 seconds, 0.446 seconds later, he's at the edge of that building. And then after that jump, so it takes, what do we say, it was 0.9485 seconds for him to jump across that gap and catch the guy. So in total, his full motion from the edge of the building to the part of the jump where he catches the man, that takes a time of 1.3945 seconds. So we just add those up. So if they want to kind of sync that up, when the man has fallen, 4.39 seconds minus 1.39 seconds. So I guess 3, I could have done that in my head. So 3 seconds. So at this 3-second time, Mr. Incredible needs to start his motion so they end up at the same location at the same time. So at 3 seconds, he needs to start running. So 3 seconds after this initial jump, he needs to start his whole thing, and then he will be able to catch him. And then this is realistic because it only takes him 3 seconds to make this run and jump. If it took more time, like let's say it took him 5 seconds to do that, this guy would have already been down here, and that wouldn't have been realistic. But because Mr. Incredible has this 3 seconds to prepare, 3 seconds to start running back here, he's got 3 seconds to catch the guy, so it does seem like this could happen in this superhero movie. Alright, and that's that one.